So, Chapter 1, the measurement of work, power, and energy expenditure. Again, very important to understanding uh, types of training we need to develop for individual athletes or the training that they're already doing. So, we can easily calculate this, and we'll get into different calculations here in a second. So, moving along to, excuse me. Okay, so first off, it is important to become familiarized with fundamental terminology. Uh, One thing about the United States is that we don't like to use what the rest of the world is using in terms of units. We use, excuse me, we use miles, feet, ounces, gallons, in Fahrenheit. The rest of the world is going to use the SI units of kilometers, meters, grams, liters, and Celsius. And there's a bunch of other various ones as well. But they're a lot easier to work with because they're divisible by 10. All right, feet, there's 12 inches in a feet. Sometimes that's a little difficult to calculate, especially in your head. You usually need a calculator with a lot of this stuff. So, so just keep in mind that there are some conversions that a lot of times in exercise physiology that we need to use to get them into quote unquote better units so that we can work with them a lot easier. So some of the abbreviations and symbols, if you look in a journal, all right, you're going to look at something like VO2 max or volume of oxygen utilized, uh, which is also your aerobic capacity. You're going to see it depicted somewhat like this. All right, so kilogram dot meters. All right, minus one exponent. Now this isn't exactly VO2 right here, but I'll get into that in a second. But what that basically means is kilograms per meter. Okay, it's not a multiplication. Well, it is actually a multiplication. It's minus one exponent is 1 over that unit. So that's where that's coming from. So when we use a per, it's recommended that we use a center dot and then a negative exponent instead of just simply using a slash. All right. It is unacceptable for the most part to use more than one slash in a single expression. Going back to the VO2 max example that I used, when we look at aerobic capacity, and we'll get into this in later chapters if you haven't seen much of it yet, is it'll be expressed in milliliters per kilogram per minute. All right, so milliliters of oxygen utilized per kilogram of body weight for every minute. Now, shorthand in the classroom and when you're writing it out, you're usually going to write it just like this. All right, just like I have highlighted ml slash kg slash minute. Okay, but if you were going to publish in a journal and write a professional, abstract or manuscript, you would write it like this. Okay. However, that does get a little confusing, and especially if you're on a computer and you're, I guess, typing fast, it's just easier to do the slashes. But just keep in mind that um, this and also this are exactly the same thing. All right. It's just this one right here is not acceptable for, say, publications. Okay. So that's why we see it that way. So if you see it that way, I'm intentionally making a mistake and doing something that's kind of out of the norm of writing a professional, abstract or journal article. So, but Almost everybody does it, so just keep that in mind. So, first we're going to look at mass versus weight. All right, and they are different. They're sometimes used interchangeably, but they are different. Mass is basically the quantity of stuff that we have. All right, the amount of matter. Then the total, and that's the total amount of subatomic particles, and it's independent of where that stuff is located in space. Okay, so gravity has no effect on how much mass a certain object has. Okay, just like the football players here, they have a certain mass associated with their bodies. Okay, and that's usually going to be expressed in kilograms or grams. And if we look at weight, it's going to be affected by the acceleration of gravity. Okay, so the acceleration of gravity here on Earth is more so than on the moon. So you're going to weigh less on the moon. You're going to weigh more here. If we were to be able to actually step foot on the surface of the sun, we would weigh more because the force of gravity is a lot more on the sun. However, our mass will always stay the same. All right, as long as we don't, lose weight, lose, burn calories and lose weight and lose fat and all that stuff. But so anyway, the base unit for mass is going to be the gram and the kilogram, like I said. Now here's the first conversion we're going to look at. So again, 1 kilogram is 1,000 grams. A kilo is 1,000. For every 1,000 kilograms, there are 2.205 pounds. Or if you want to shorten that and use 2.2, that's perfectly fine. So therefore, if you weighed 150 pounds, to get that into kilograms, simply divide by 2.2. All right, so you get about approximately 68 kilograms. Now, if it were kilograms and you wanted to figure out how much you weighed in pounds, multiply that by 2.205. Now, looking at length, it's going to be expressed in either meters or centimeters, which is a hundredth of a meter, and kilometers. And here's our second conversion. Is a lot of times we'll see measurements in inches, and we need to be able to convert that into centimeters. So for every inch, there's 2.54 centimeters. So if we had 2 inches and we wanted to figure out how many centimeters that was, just multiply by 2.54. Just like the example right here. All right, so we have 70 inches if you're 5 foot 10 inches tall. Multiply that by 2.54, you get approximately 177.8 centimeters. And then if we wanted to convert it into meters, and really the only one of the only times that you'll see that in health and physiology is in BMI calculations. The BMI calculation, or the body mass index, you want your height in meters. Okay, so that's really the only time, for the most part, that you're going to see that. Usually, it's going to be in centimeters. So, so just divide it by 100, and you have meters. Now, looking at volume, instead of using gallons, we're going to use liters. All right, and also milliliters. And every once in a while, you'll see cubic centimeters or cm, the third power, or cc's. All right, and that's equivalent to 1 milliliter. All right, we often use it when we're measuring VO2 or your oxygen consumption during exercise or during rest as well. Can also look at it during sweat losses. How many milliliters of fluid are you losing? How much fluid are you putting back into your body? Then also lung capacities. So let's start looking at force and also work output and power. Excuse me. So a lot of times when we're looking at force, one thing we think of right away, or at least I do, maybe you don't, but I think of force production and strength training. So you're going to look at muscular strength and also the power output. But we can also look at that during an aerobic type activity as well, and we'll see that here in a few slides. So force is going to be equal to mass times acceleration. All right, that's one of Sir Isaac Newton's laws of motion. All right, and it's actually one of the units that can be used is 1 Newton. And that's equal to the force required to accelerate a 1 kilogram mass at a rate of 1 meter per second. All right. So F equals ma is one of the first equations we're looking at, and then again 1 Newton is equal to 1 kilogram meters, or 1 kilogram per meters per second. All right. So looking at work and energy, sometimes we'll use joule for the unit for work, and work is simply force times the distance. Okay, remember force equals mass times acceleration, and if you multiply the distance traveled, then you're going to get the work. So, for example, if a 5 Newton force moves a ball a distance of 2 meters, the work that it took was 10 Newton meters. If a 5 kilogram mass moves a distance of 2 meters, it's 10 kilogram meters. And 1 joule is going to be equal to 1 Newton meter. Okay, so looking at energy, so this is the body's ability to perform work and generate heat. And just not the human body, a lot of mechanical devices will generate heat as well. The human body, we will generate most of the energy production uh, that we bring about. That's going to be converted into heat. All right, less than half of it is actually going to be used for work output. So we're creating a lot of heat when we're exercising. And when we look at it in nutrition and also in exercise, we look at calories that we burn. All right, and a small c calorie that we see here is not the same as what we see on the side of a milk carton or a cereal box or a bag of potato chips. All right, this is 1,000th of one of those calories. Those are actually referred to as big C calories, okay, and also known as kilocalories. So if I use the term kilocalories, or if you see this abbreviation right here, that's simply just one big C calorie, and that's equal to approximately 4,184 joules. Now, one point I do want to make in terms of energy production, when we intake food, we don't convert anything to energy. We're breaking bonds of either carbohydrates or fats or proteins or alcohol. Alcohol is actually another one of the energy producing nutrients. We actually break those bonds and we're able to transfer energy into something else, create a new product, use it to form ATP, and then we break ATP, and we'll get into that later on as well. But if we actually converted something to energy, this is what we would have: E equals mc squared. And I'm sure most of you have seen that before with Albert Einstein, and that's energy equals mass times the speed of light squared. So 1 gram of a certain material is going to be 21.5 billion kilocalories. We would generate a lot of heat if we actually converted our food to energy. So we're just transferring the energy. Okay, looking at power. Power then is going to be equal to work divided by time. So how much work you're able to do in a certain amount of time. If you keep the same time and you increase your power or increase your work, then your power is going to increase. Oh, excuse me. I was kind of messed up there. Kind of one of those late nights. Okay, so start again. Three, two, one. So looking at power, power is going to be equal to work divided by time, or the amount of work in a certain amount of time that you have. So you can increase your power if you do the same amount of work in a shorter period of time. All right, and the units for these, some common ones are going to be watts, joules per second, and then also horsepower. All right, most used in car engines. Um, for our examples, most of what we're going to use is going to be wattage. All right, how many watts we're producing. So, looking at work and power in terms of how we measure it and how we determine how much energy someone is producing and how much work they're putting forth and power output, we have certain devices that we can look at: an ergometer, and we can measure it by ergometry then. So an ergometer is just a device used to measure work, right? And then ergometry is measurement of work output. We have 4 examples down here, and these are pictures from the book. So the first one here is a step ergometer. You can see these in step aerobics classes. Normally they're going to be about zero point 0.3 meters off the floor. Then we have a cycle ergometer, the second one from the left. And this is a Monarch bike. And if you look at the pointer that I have right there, you can add weights to that. If you haven't seen one before, uh, or if you've seen one and you weren't really sure what they were for, you can add resistance to the flywheel here. And other bikes will have other ways of doing it. You can have turn knobs. It can even be electronic as well. So adding resistance to the flywheel. Then we have a treadmill ergometer. I'm sure most of us have seen that as well. Then an arm ergometer also. So let's look at some equations here or some examples that we can look at how much work and power someone is producing. All right, so one of the examples in the book was a 70 kilogram subject on a bench step ergometer. So say they're in a step aerobics class, okay? And that height of the step is zero point 0.3 meters. And they're stepping up 30 times per minute for 10 minutes. All right, that exercise bout lasted 10 minutes. So if we want to look at work, again, work equals force times the distance. So the force then, 70 kilograms, and they were actually converting it into newtons. So that's where the 9.81 newtons per kilogram comes from. All right, so they were converting it into newtons. So for every kilogram, there's 9.81 newtons. So we have the newtons at 686.7. The distance then that they were stepping was zero point 0.3 meters for every step, and they had 30 steps per minute. And then the entire exercise lasted 10 minutes. So if we just multiply zero point 0.3 times 30 steps times 10 minutes, we get 90 meters. So then for the work, we just simply multiply the force that we generated, the newtons, times the distance in meters. So 686.7 times 90 is equal to 61,803 joules. All right, because remember, 1 joule is equal to 1 Newton meter. If you wanted to put it in kilojoules, it'd be approximately 61.8 kilojoules, and that's simply dividing the joules by 1,000. So then we want to figure out the power output. Just take the amount of joules divided by seconds, or a certain time unit. If you wanted to do minutes, you could do it in minutes as well. But the example in the book was seconds, so it was 103 joules per second. Or 103 watts. Whoop, let me go back real quick. All right, so hold on, let me figure this out. Okay. Now instead of converting it into newtons, we can keep it in kilograms. All right, and then we can still get it into watts. All right, so if we just take the 70 times 0.3 meters times 30 times 10, that's still force. That kilogram we can use as force times the distance that they traveled. We will get 6,300 kilogram meters. All right, and then the power then is just the work divided by the time. So 6,300 kilogram meters divided by minutes. So we get 630 kilogram minutes or kilogram meters per minute. Now that is all well and good, but in terms of a unit that most bikes and ergometers are going to be calibrated at, or at least units that are on the bike that you can set it to, or a treadmill if you want, and then also a bench step. Most individuals aren't going to know what a kilogram meter per minute is, but they'll be able to at least understand a little bit about watts. Okay, so if we look at 1 watt, and this is from the book, in table 1.4, 1 watt is going to be equal to 6.12 kilogram meters per minute. Or there's going to be 6.12 kilogram meters per minute in every watt. So if we simply divide by 6.12, we get 103 watts. And again, 1 watt is equal to 1 joule per second. Now, if you wanted to do the other one down here on the bottom, if you wanted to multiply by 0.163, it would give you approximately the same number. There's going to be a slight error there, but it's not going to be, it shouldn't be so significant that it's going to completely throw it off. So that 6.12 is going to be a conversion that we'll use here in the next couple slides as well. So let's look at a stationary bicycle or a cycle ergometer. So it can be variable resistance. That's one of the benefits of it. It's useful in training applications. You want an athlete to increase their power output or their work output. You can just simply increase the resistance on the flywheel, and therefore they'll be working harder. All right, as long as they're keeping up of their revolutions per minute. So here's an example, and it's straight from the book again. Subject exercises for 10 minutes with a resistance of 1.5 kilograms on the flywheel. All right, there's usually a belt or some type of device that's able to add resistance to the flywheel. All right, and then that distance on it is 6 meters, and they're going to be pedaling at 60 revolutions per minute. So if we look at the work, we have a force of 1.5 kilograms multiplied by the distance. So we have 6 meters for every revolution. And every minute we have 60 revolutions. And the exercise lasted for 10 minutes. So we have 5,400 kilogram meters. So then we just divide that by 10 minutes to get the power, which was equal to about 88.2 watts, which originally came out to 540 kilogram meters per minute. But again, if we divide that by 6.12, we get 88.2 watts. Okay, so here's one that you can try for yourself, and I'll try to put up a couple more examples of these. So a subject cycles for 30 minutes on a cycle ergometer for at 2.1 kilograms of resistance. The flywheel distance is 6 meters again, and they pedal at an average RPM or revolutions per minute of 52. So then how much power does the individual generate? So look at the work. We've got 2.1 times the distance, so that's 6 meters for every revolution. And for every minute we have 52 of those revolutions, and the exercise lasted 30 minutes. So 19,656 kilogram meters. And if we divide that by 30 minutes, then the amount of time that work was produced, we get 655.2 kilogram meters per minute. And if we divide that by 6.2, again going back to the conversions, we get approximately 107.1 watts during this 30-minute exercise. Looking at a treadmill, the one big difference in a treadmill is that there's going to be a percent grade. It's tough to calculate if it's flat or horizontal, but the good thing about a treadmill is you can increase the resistance somewhat by increasing or decreasing the slope. All right, and we're going to look at it in terms of a percent grade. And a percent grade is just a change over 100 units. So If the change over 100 units was 7.5 meters over 100 meters of horizontal distance, that's a 7.5% grade. So, and we're going to express these in fractional units when we multiply this out. So, looking at it, we have a 60 kilogram individual, and they walk at 200 meters per minute on a treadmill at 7.5% grade for 10 minutes. So, the work is going to be 60 kilograms times 0.075, and that is our percent grade, times 200 meters per minute times 10. So again, it's still the force times the distance, but we're also figuring out and correcting for the percent grade. So our work output is 9,000 kilogram meters, and just like we did in the psychoergometry calculation and also the step test, or um, the bench step ergometer, when we look at power, we have to divide by the amount of time that work was produced, and we get 900 kilogram meters per minute. And if we look at the conversion table and divide by 6.12, we get about 147 watts. All right, so let's change gears a little bit and talk about energy expenditure. So there's going to be two types of ways we can figure out how many calories we're burning or how much heat we're producing. Going to be direct and indirect. And indirect actually is going to be an easier way of doing it, but we'll go over direct calorimetry so we can get that out of the way right now. It does require uh, quite a bit of money to create a room, an insulated airtight chamber. And what's going to be happening is there's air circulating, or there's water circulating in the walls, and it's going to be colder water. Then the heat produced by the body then is going to radiate out to the walls and warm the water up. And then from there you can determine how much heat the body is producing. It actually kind of falls apart once they begin to exercise, because as you begin to exercise, you sweat, and the heat transfer is going to be greater because of the sweat. And that's one of the benefits of sweating, is that we can transfer heat better to the surrounding atmosphere. And I did mention this earlier, that 60% of energy that we produce from the substrates, the carbohydrates, the fats, the proteins that we intake into our bodies and store and then break them down and use them for energy, it's mostly generated as heat. And only about 40% of it is actually used for ATP, or adenosine triphosphate, which is going to be where we get the energy. So here's an example of direct calorimetry, and again, it shows this lady working out inside this chamber. However, there is going to be some air because she's going to be sweating. So again, there's going to be some type of coolant, in this case cold water, inside the walls, and as that heats up, you're able to determine the amount of heat and energy produced. So indirect calorimetry, this is going to be based on the amount of oxygen that we use and also CO2 that's produced. And from this, we can get what's known as respiratory exchange ratio, or RER. And this can be an indirect way of looking at the gas exchange at the cells, and also the ATP production, our high energy phosphate production at the cells. However, this is going to rely on simply the aerobic system. There are three ways or three systems that we use in the body to get energy, and two of them are anaerobic. All right, don't need oxygen for them to actually produce the energy, but they're always running. They're always going to be producing ATP and producing energy. But indirect calorimetry is only going to calculate how much we're getting from the aerobic. So that's one of the errors within indirect calorimetry. So our oxygen storage in our body, we have a little bit, but there's not a lot. It is fairly really limited. So we can accurately determine oxygen usage, and this is by way of a metabolic cart, a VO2 max cart. If you've seen one, you can also indirectly estimate for VO2 max, and you can somewhat calculate there as well. For every liter of oxygen that we consume, there's going to be approximately 5 kilocalories produced. All right, and this is going to vary depending on whether it's fats that we're burning or carbohydrates. And here's a picture. Looks like a somewhat of an older picture of a metabolic cart. Again, the hoses are coming in. More than likely, this hose, if you can see the pointer, is going to be the intake. And then as they breathe out, there's going to be one-way valves in this mouthpiece. It's going to blow the air, the expired air, through this tube into here. And there's going to be gas tubes, which is the air that they're breathing in, known as the gas, going to go into this machine, figure out the amount of oxygen and carbohydrates that they're exhaling, and from there the algorithms within the computer is able to tell how much oxygen and carbohydrates or and carbon dioxide that they're using. So we can get an important ratio then that we're going to look at, which is RER. Again, respiratory exchange ratio, and it's also known as RQ, or respiratory quotient. So RER is simply the volume of carbon dioxide divided by the volume of oxygen. All right, and RER is at the lungs. The RQ is going to be at the cells. All right, when we hook someone up to a metabolic cart, this is what we're going to be getting. All right, we're not really going to be getting RQ, but we're going to be getting RER. And where that comes from is that if we have an RER of 1, so that ratio of VCO2 and VO2 is 1, it's going to be coming from this equation right here. So if we have or if we're burning simply just glucose, we're going to be producing 6 carbon dioxides and 6 oxygen molecules. If we're burning fats and we have a RER of 0.71, such as in palmitic acid, which is one of a fairly large fatty acid, we have 16 carbon dioxide molecules versus 23 oxygen molecules. So therefore we have an RER, or a respiratory exchange ratio, of 0.71. All right, so it's simply a division of carbon dioxide divided by oxygen is the RER. So we can use this RER to look at specific caloric equivalent of oxygen consumption. And then a portion, or the percentage of energy, then derived from fats or carbohydrates. Carbohydrates, we get 6.3 ATP or those high energy phosphates, for every oxygen molecule. So, which is equal to approximately 5.05 kilocalories for every liter of oxygen that's consumed. If we look at fats, we only we only get 5.6 ATP for every oxygen molecule, right, which is about 4.7 kilocalories per liter of oxygen. So if we look at a fat molecule, so more oxygen is used to metabolize fat, but we're going to get more energy out of every gram, or equal amount of fat compared to carbohydrates, which actually breaks down to fats. We get approximately 9.5 kilocalories for every gram of fat we burn. Carbohydrates, we get 4. All right, so let's look at this exchange ratio table here. So again, well, let's first look at RER, because that's the most important thing. This is what you're going to be looking at first, is the RER right here. So if we have, again, an RER of 0.71, we're burning all fats. If we have an RER of 1, we're burning all carbohydrates and no fats. So if we have an RER of 0.85, we're getting approximately 50-50 from fats and carbohydrates. It is a little bit more for carbohydrates. So this is the percentage of kilocalories coming from either fats or carbohydrates. Now, sorry about that. 3, 2, 1, go. All right, so if we look at the energy, so for every liter of oxygen that we consume, this column tells us how many kilocalories we're actually producing, all right, in total. All right, so let's get to it and look at an equation. All right. So if we have a VCO2 of 4.25 liters per minute, and we have a VO2 of 5 liters per minute, and we want to figure out what the energy expenditure rate is, we simply divide 4.25 divided by 5, so VCO2 divided by VO2, and we get 0.85. So let's go back to the chart real quick. So we have this RER of 0.85. And for every liter of oxygen, we're getting 4.86 kilocalories, all right, in total. Okay? So 4.86 kilocalories for every liter. So we're using 5 liters. So we simply multiply 5 liters of oxygen that we utilized times 4.6 or 4.86, and we get about 24.3 kilocalories per minute. And that's how much energy that we're producing for every minute. that we're exercising at this rate. All right, this VCO2 of 4.25 and VO2 of 5 liters per minute. Now, if you haven't seen how we've gotten this, if you haven't um, seen a VO2 max cart, it's just a print off. I mean, it comes right up on the screen. You can somewhat estimate these through various other ways, but most of the time you're going to need some type of metabolic device, some type of cart where you're able to breathe into and it's able to calculate what the VCO2 and the VO2 is. All right, but this is indirect calorimetry, and this is usually how it's done. You usually need a metabolic cart to get it done, but there is another way we can do it. Uh, we'll, um, we'll look at that here in a second. So then, if we wanted to figure out, well, how many carbohydrates were they burning, or how much calories were coming from carbohydrates? So again, we have the RER of 0.85, and let's go back to the table. RER of 0.85, and we have 51% of the kilocalories coming from carbohydrates. We have 49% coming from fats. So let's go back. All right, so 51% coming from carbohydrates. So we take 24.3 kilocalories per minute and multiply that by 51% or 0.51, and we get about 12.4 kilocalories per minute, or 12.39 to be precise. Okay. So what's the energy expenditure from fats? Well, you can do a simple subtraction if you wanted to, but if you didn't know carbohydrates and you wanted to just look at fats, you multiply that 24.3, that total amount of kilocalories, by 0.49 or 49%, and you get about 11.91 kilocalories per minute that is going to be coming from fatty acids. So then if the exercise bout was 10 minutes long, we can figure this out in just simple multiplication by those 10 minutes. All right, because the units that we have is kilocalories per minute, so if we knew how many minutes they were exercising, we could figure out how many calories they were burning. Or if they had a goal of a certain amount of calories that they wanted to burn, you could figure out how long they needed to work at that certain workload. So the total energy contributions from carbs for that bout, then take the 12.39 times 10 minutes, you get about 124 kilocalories. And then from fat, you get about 120. So again, about 50-50 for that. But on the exam, I will have this chart. Okay. So I'm not going to make you memorize this or anything like that. And it's kind of not really practical to memorize something like this. If you happen to go into a situation where you use it a lot, I mean, you might actually just know them. You might learn them offhand. But in some charts, some tables, you'll actually see them. They're a lot more detailed. So for instance, instead of 0.71, then the next one will be 0.75. It'll go to 0.72, 0.73, 0.74, then 0.76, and so on and so on. But I will give you this table, or at least give you the file for it so you can download it while you're taking the exam. So we ended right here. So again, we were able to figure out how much from carbohydrates and fats we were burning in terms of kilocalories for that 10-minute exercise. So some of the limitations is the carbon dioxide that's produced may not equal CO2 exhalation. All right. The exchange within the lungs of the carbon dioxide that's produced in the blood, you need to exhale that. Sometimes that isn't going to be exchanged as well as it should be. So the numbers that you're getting from that exhaled air in um, the metabolic device that you're using is calculating that they may not be the same. All right, and then the exchange at the lungs and also the cellular level might not be the same as well. RER is inaccurate for protein oxidation. Protein is not a great energy substance. That's why low carbohydrate diets are really a bad deal for athletes. If you've ever been on a low carbohydrate diet, more likely you're eating a lot more protein. You're also eating a lot more fats as well. But you're eating a lot of protein, so your body tries to use that protein for energy, and it doesn't work all that well. And one reason why the RER is inaccurate for it is because there's a lot of energy lost with protein utilization for energy through excreting the nitrogen, because we don't use the nitrogen unless we're building the muscle. That's in a different um, pathway. So we want to get rid of the nitrogen, and there's actually energy that's used to get rid of it. So, and they're not really sure exactly how much. It's tough to actually calculate that and figure it out. So that's why it becomes inaccurate. An RER near 1.0, it may be inaccurate because when we look at lactate, and we'll get into this in chapters 3 and 4, I believe, biochemistry and also bioenergetics, it can also cause increased carbon dioxide exhalation. All right, because your blood becomes a little bit more acidic, and to neutralize that, you're going to be hyperventilating a little bit. So you're going to be increasing your CO2 exhalation. Then gluconeogenesis, which is the making of new glucose or new carbohydrates, produces an RER of less than 0.70. All right, in most of the charts, most of those tables are not going to go below 0.70. Okay, and then again, like I said before, it ignores the anaerobic energy systems, and we'll get into the different energy systems next week, or I guess for the online class when I get them up. Hopefully sooner next week, but it's been a busy week. Please bear with me. So looking at the basal metabolic rate, there's a bunch of different equations. If you've taken a nutrition class, you've probably seen a couple of them. One is the Harris-Benedict equation, where it takes into account your height, your weight, your gender as well. And your basal metabolic rate, or your BMR, is just a minimum required energy used to live. All right, to stay alive. And but it doesn't account for exercise or any of your daily activities. And if you use something like the Harris-Benedict equation, uh, we might get into that when we get into the nutrition chapters, but not right now. But if we use some of those equations, we have to we have to factor in daily activities and daily exercise if we want to look at maybe a nutrition program. All right, and usually you multiply it by maybe 1.3, 1.5, or 1.7, depending on what the activity is. And there's some tables and some rough estimates of what you need to multiply that number by to get a rough estimate of your daily caloric expenditure. And muscle has a high metabolic rate, and this is one of the main reasons why men tend to have a greater BMR than women. Is that men have more testosterone, therefore they have a much greater muscle mass, and the body needs to utilize more energy to maintain that mass, so therefore they have a higher metabolic rate. So then some factors affecting BMR then, uh, not only gender, I mean not always. If you have maybe a female bodybuilder and a male individual that is kind of weak, if you will, that Female is probably going to have a higher BMR. Um, but all things being equal, men are going to have a little bit higher BMR. Your age, it will also decrease with age. And along with age, you decrease your muscle mass. So if you decrease your muscle mass, you're going to be decreasing your metabolic rate. Body temperature, if you increase your body temperature, you're going to increase your basal metabolic rate. And psychological stress plays a large role. A lot of research in the past 10 or 15 years or so has looked at how the mind kind of dictates what your metabolism is and what's going on, what hormones are released during certain stress periods, and how that affects how your body metabolizes your energy stores or stores extra energy. And then also different hormones that are released as well. So here is a way of kind of roughly estimating. If you don't happen to have a metabolic cart, you can somewhat estimate what someone's caloric, I guess, basal metabolic rate is. If you're just sitting there, maybe lying down, sitting in a chair, relaxing, um, just a nice, calm breathing, there's going to be approximately 3.5 milliliters per kilogram per minute utilized. And what that means is for every kilogram of body weight or body mass, that individual is going to be utilizing 3.5 milliliters of oxygen, right, for every minute. And 3.5 ml per kg per minute is equal to one metabolic equivalent. And let me actually write this in here as I think that's how you spell equivalent. Okay, so that's equal to one metabolic equivalent. All right, and it's relative to body mass. Okay, ml per kg per minute is what is known as relative VO2. All right, so it's relative to what your body mass is. If you wanted to put it into absolute, that's liters per minute. That is not based on your body mass. That's just overall. Okay, that is just liters per minute. That's it. No kilograms, no grams, no nothing. So, for example, if you had a male athlete and his body mass was 100 kilograms, and one met is going to be approximately 3.5 ml per kg per minute. And again, this is an average for everybody. It's not, there's been some studies on this of what an average individual is going to be utilizing in terms of oxygen for every minute at rest, and 3.5 is average. Okay, some might be lower, some might be a little bit higher, and that's why this is a estimation. It's not a great calculation, but it's a good estimation. So if we want to get it into absolute, we can multiply by 100. So 3.5 times 100 equals 350 milliliters per minute. And then if we want to get it into liters per minute, which is normally the units that we use for absolute, we simply divide by 1,000 and we get 0.35 liters per minute. Now, also on average, an individual is going to have a resting RER of 0.85, about. Okay, it's not exact. Again, it might be higher, it might be lower, but on average, it's about 0.85. So we can look at this individual, and if we go back to that chart, and let me go back real quick. I don't want to. Okay, don't want to be giving you some eye gymnastics to do as I'm flipping through here, but if we go back to this chart again, we go to 0.85, and we look. We have 4.86 liters. 4.86 kilocalories for every liter of oxygen utilized. And keep in mind we have that 49% fats and 51% carbohydrates. And let's go to here. So that 4.86 kilocalories for every liter of oxygen, and they were used. And then this number right here is the oxygen that's utilized. Again, this is at rest. So 0.35 liters, and we multiply those. It's 1.7 kilocalories for every minute. And the liters disappeared because they multiplied out. So we can take this even a little bit further. And if we look at one complete day, if that person just rests and looked, if we want to look at their metabolic rate through one day, there's 1,440 minutes in each day. So if we take 1.7 times 1,440, we get 2,448 kilocalories for every day for this 100 kilogram male. And again, breaking down those calories a little further, 51% from fats and 49% from carbohydrates. 1,248 for fat and 1,200 for carbohydrates. Now, the book also talked about percent net efficiency. All right, so like I said before, humans lose most of the energy to heat production. All right, only about 40% of what we generate is going to be used for actually work and power output. Most of it is going to be for heat production. So we can look at our efficiency in terms of work divided by the energy expended. All right, how many calories we were burning, or how many kilocalories we were using. And then multiplying that by 100, then we can get a percentage. So it's just how efficient somebody is, or how the human body is. At low workloads, at low to moderate workloads, or exercise intensities, you're going to have a pretty good net efficiency. But at a higher intensity, if you're working near maximum intensity, your net efficiency is not going to be all that great. You're going to have a really high energy expenditure versus your workload. So, or a really high work output versus your energy expenditure. 3, 2, 1. All right, I'm going to fix this real quick because I forgot about this, and as I was going along, I had forgot to fix it. So, looking at the percent net efficiency, you need to calculate the work and also the VCO and also the RER, which is the VCO2 divided by the VO2 during steady state exercise. All right, in steady state exercise, as we'll get into homeostasis in the next chapter, is your heart rate, your blood pressure, your breathing all stays relatively constant. All right, it can't be in the middle of increasing or decreasing. All right, it has to be relatively constant for a certain amount of time. Okay. So, and that's all I have for chapter 1. We'll be uploading chapter 2 shortly as well. And if you have any questions, please let me know. If I'm going too fast in these, please drop me a line and an email. If I'm going too slow, let me know that as well. So, anyway, I will upload chapter 2 soon. Thank you.